एवरीवन, कैसे हो आप सभी लोग? आई होप सब अच्छे होंगे. So I'm back again with the video lecture on the topic of binomial theorem, lecture number 6. So in this today's problem lecture, we will basically talk about the revision that we did in the previous lecture. So if you haven't watched the previous lecture of this binomial theorem, I will suggest you to go to the playlist of the binomial theorem in the description box of today's video, and you will find that playlist of the binomial theorem. Watch the previous lecture and then start watching this particular lecture. So in today's lecture, we will solve questions on the series of binomial coefficient, and we will study a new topic, that is binomial for any index. Okay. Now up till now, we already studied our binomial for an index, which is basically an integral number. Okay, or a natural number to be very specific. But now onward, we will study about binomial for any given index, that may be non-negative as well. Okay, so let us study about those topics. So before moving further, let us take a small recap of the concepts we have already covered till now. Okay, a small recap. Okay, so let us move further. So what we studied till now is the summation of r given 0 to n. Okay, r given 0 to n of the all the binomial coefficient NCR is basically equal to 2 to the power n. Okay, so this is the very first thing that you must remember. And the second summation of series that you must remember also is basically r given 0 to n, that is r multiplied with NCR is basically equal to n into 2 to the power n minus 1. Now these two things are very crucial, and you can think of, like, you can remember it for your purpose of like solving question quickly. Okay, because many times you're not able to go back to the derivation part and then take out what the result is. So it is better to remember and do the questions. Okay, so we have already established our concepts regarding those particular, how to solve questions on the binomial series. Okay. Okay, so we have already seen about that first method, that was the methods we were using was, okay, the first method we were talking about was the general term method. Okay, we were trying to find out the general term of that particular given summation, and then we were applying the sigma on that. The second method that we looked about is the differentiation method. Okay, so in order to get the result from the differentiation method, we were first thinking like which particular series or expansion will yield the definite result. Okay, and then we were thinking of, like, after differentiating this particular term, we will get to the corresponding result. And in today's lecture, we will be talking about the third method, that is the integration method. Now, many in time of the binomial series expansion, you will find questions which will have binomial coefficient. In the denominator term, there will be some variable terms. Okay, so those types of question can be approached by the integration method. Okay, because why is this particular method known as integration method? Because we know that the integration of x to the power n dx for n not equal to minus 1, for n not equal to minus 1, we know the indefinite integral. For n not equal to minus 1, we know this indefinite integral is basically x to the power n plus 1 divided by n plus 1 plus some constant. Okay, so we can use this particular whenever we'll have series expansion of binomial series with the variable terms in the denominator. We can think this particular approach by the integration approach. Okay, so let us get started with today's particular lecture description with some question. Okay, so beginning forward, let us solve some question to get an idea. Okay, so the very first question I have taken up on the screen is a question from the previous year J advanced paper. Okay, now this is very interesting type of question. Okay, and it doesn't involve lot of thinking. It involves a little bit of thinking, but if you're once able to think that particular approach, then you are basically, this question is nothing but just a cakewalk. Okay, so this is the first example. Let us solve this. Okay, so let us try to solve this particular question. So what is asked in the problem is that we have given with a series. Now I am calling this particular summation as S, and it is asked that, it is also said that NCR can also be written like this particular fashion. Okay, so what is said, it is asking you the summation of 30C0 and 30C10 minus 30C1 into 30C11 30C2, okay, into 30C12, okay, and so on up to plus 30C20 multiplied with 30C30. Okay, so the question that is asking you the summation of this particular series. Okay, so how will we approach this particular series? But let us try to understand what these all terms are generating. So if you see the denominator part. Okay, so if I can also write this particular as 30C0 into 30C20. Okay, because we know the property that is NCR is also equal to NC n minus R. Okay, so NCR is also equal to NC n minus R. So similarly, we can also write this particular thing as 30C1 into 30C19. Now this particular summation or the series also will be remembered as form of a formula which I will be talking about in the after solving this particular problem. Okay, plus 30C2 into 30C. So you can write this as 30C18. So what is the advantage of writing like this? Why did I write like this? Okay, you can write this as 20 and into 30C0. Okay, so what is the advantage of writing like this? You will understand that if you sum up the lower indices of this binomial coefficient, you will always get a constant summation. You will always get a constant summation. Now this will be a trick, or the trick that you will be using to solve this particular problem. Now what can I understand from here? That however you take this particular thing, you sum up the lower indices is always 20. The lower indices are always 20. Now the idea that I want to establish in all of your mind is that whenever we are looking for coefficient of x ki power r in the expansion of 1 plus x ki power n, we always get the coefficient of x ki power r as ncr. Okay, so if you think of like if we are given with some kind of expansion like 1 plus x ki power n1 and 1 minus x ki power n2, and then we are talking about we have to find some coefficient of r, then what we can do, we can take n1 minus r from here. Okay, we can take, I'm sorry, we can take n1 minus r from here, and similarly we take n1 minus r from here. So because we are looking for the coefficient of maybe we'll let us tell like this fashion that we are looking for the coefficient of n. Okay, x ki power n. So if we take x ki power n from here, then we take x ki power 0 from here. Similarly, if we take n minus 1 from here, then we take x ki power 1 from here, and so on we go on fashion. Okay, so this particular problem is also very similar to this particular question that is given in the problem statement. Okay, that is a summation, that is S. So what is this particular S? Now we can also write this S as coefficient of, okay, coefficient of, now what we see the lower index is summation as 20. So it is the coefficient of x ki power 20 in the expansion of 1 plus x ki power 1 plus x ki power 30, because the first binomial coefficient has the upper index 30, the second also has 30. So it can be written as coefficient of x ki power 20 in the expansion of 1 plus x ki power 30 into 1 minus x ki power 30 into 1 minus x ki power 30. Okay, so if you look at this particular expansion, that is, okay, that is 1 plus x ki power 30 multiplied by 1 minus x ki power 30. So if you look for the coefficient of, if we have to look for the, if we have to look for the coefficient of x ki power 20, how we will get it? We'll firstly try to get the coefficient of 20 from here, that is 30c 20, and we'll get x equals 0 from here, that is 30c 0. Okay, and similarly we have to get 20, so we can do this 19 from here and 1 from here, so we'll get 30c 19 into minus 1 raised to the power 1 into 30c1. Okay, and so on we will generate the series. So this series is very similar to the series that is asked in the problem, that is the problem that is S. So we can talk about the S is basically nothing but the coefficient of x ki power 20 in the expansion of 1 plus x ki power 30 into 1 minus x ki power 30, that can also be established as 1 minus x square whole raised to the power 30. So if we have to look for a coefficient of x ki power 20, what we can say about it? It will be basically 30c10 minus 1 ki power 10. Okay, so this result will be yielding you 30c0. Okay, 30c10, sorry, 30c10. So the answer to this particular problem will be equal to 30c10, or it can be written as the summation. If we call this particular summation, then the summation will be 30c10. Okay, 30c10. That's the required answer of this particular problem. Okay, that's the answer of this particular problem. Alright, so this was a single correct type problem, and you were given with the four options. You have to match the correct option. Okay, I hope this particular thing is clear. Okay, so this particular thing you can solve it on your own. Okay, so let us move further and let us study about the new methods that we were discussing or wanted to study about. So the very first thing that we wanted to know about the today's particular description, because we already talked about the general term, we have talked about the differentiation method. Now only method that was left is basically the integration method. Okay, so that when do we need to use the integration method? The question, so for example, you have a binomial series. Now I'm giving you again saying that C0, C1 are all the binomial coefficient of the expansion of 1 plus sk power n. Okay, so if we are given with this particular binomial coefficient, and then you are asking with the summation as C0 plus C1 by 1 plus C2 by 2 plus C3 by 3 and so on up to Cn by n plus 1. I'm sorry, this will be C1 by 2, C2 by 3, okay, and C3 by 4. Okay, so this will be C1 by 2, C2 by 3, C3 by 4 and so on up to Cn by n by 1, n plus 1. Okay, so this was the summation that is required to find this particular problem. Okay, so how we will basically deal with this particular problem? Now, the very first method that I will firstly discuss is the general method. Okay, the general term method. Okay, now I will basically try to hinder you or try to give you in your mind the idea like how to establish this particular problem. Now I've already given you the idea why do we need to use the integration method, because whenever we integrate x to the power n, the result is x to the power n plus 1 divided by n plus 1. So what we try to see is if this is the rth term, what is the denominator part is r plus 1. So whatever is present in the rth term, the denominator has r plus 1 in it. Okay, so the denominator always has r plus 1 in it. So if we look for the general term, the general term looks like CR r plus 1. Okay, NCR divided by r plus 1. So what is the summation that is asked? That is summation of r belonging from 0 up to n, that is NCR divided by r plus 1. Okay, so this is the required summation that we need to find in this particular problem. So how to solve this particular problem? Now let us write this particular summation as 1 by r plus 1 into CR. Okay, so what I will try to generate in this particular fashion is that I will try to multiply and divide by n plus 1, because it is n over here. So I will try to multiply as well as divide by n plus 1. Okay, so if I multiply with n plus 1 divided by r plus 1 also, then I have to divide by n plus 1. Okay, so there will be a sigma sign over here, r is equal to 0 up to n. And in doing so, what will we get? We already studied about one very important result, that is NCR can also be written as n by r multiplied with n minus 1 c r minus 1. Now this is a very important relation that we studied in the properties of binomial coefficient. So if we apply this particular result, if we take n plus 1, because it is a constant term, so let us take this particular out of the sigma. So it will generate 1 by n plus 1 into sigma r belonging to 0 up to n. Okay, r belonging to 0 up to n plus 1 divided by r plus 1, okay, whole multiplied with NCR. So if we see this particular term, what this particular term is, this particular term is equal to n plus 1 into sigma r is equal to 0 up to n. This particular term is nothing but n plus 1 c r plus 1. Okay, by using this particular property of recursion property. Okay, so in doing so we get this particular relation. So what is this particular relation if we try to expand this? So in order to try to expand the series, okay, so what the series was looking up till now is 1 by n plus 1 into sigma of r is equal to 0 up to n plus 1 c r plus 1. So this particular relation is nothing but equal to 1 divided by n plus 1. So if we expand this, we'll get it as n plus 1 c 1 plus n plus 1 c 2 and so on up to n plus 1 c n plus 1. So what we look at this particular problem is that this particular series only lacks one particular term in order to complete that particular formula of 2 raised to the power n plus 1. So what particular term is left? The term which is left is basically n plus 1 c0. So if I added this particular term n plus 1 c0, then my responsibility is also to substitute this particular term, that is n plus c0. And we know that nc0 or n plus 1 c0 or c0 is basically equal to 1. Okay, so what will be the final result is? So if we look at this particular series, and if we take this particular series, what this series will result in? This particular series will result in 2 to the power n plus 1. So the answer to this particular problem will become 2 to the power n plus 1 minus 1 whole divided by n plus 1. So this is the first method, that is the general term method of solving this type of problems. of solving this type of problem. I hope this particular approach is clear. Okay, so what approach did I use? I approached only, that is, I divided and multiplied with n plus 1, and in doing so, what I get this I use this particular property, and then I get this particular direct result that we already know, or that we already know as 2 to the power n plus 1. Okay, now the second method that I was talking about was the integration method, or an approach of integration approach. Okay, so let me write it down as the integration approach. Okay, so the summation that was given to us in the question was C0 plus C1 by 2 plus C3, sorry, C2 by 3 plus C3 by 4, and so on up to Cn by n plus 1. Okay, so this was the summation that was given in the problem. So let us in order to solve this by the integration problem, let us again use the, let us take help of that particular integration method, the expansion. Okay, so in the expansion of 1 plus x to the power n is equal to C0 plus C1x plus C2 x square, and so on up to C3 x to the power n, sorry, Cn x to the power n. So this is Cn x to the power n. Okay, now what I try to do in this particular thing is that if I integrate this both the sides, so on integrating both the sides, on integrating both sides, we get, what do we get? The result we get 1 plus x to the power n plus 1 by n plus 1, okay, plus the constant, okay, plus the constant c. So this was the integration of this particular. If we integrate both the side with respect to dx, okay, so if we integrate both the sides with respect to dx, we end up with getting this particular result, and is equal to c1x plus c1, sorry, c0x plus c1 x square by 2 plus c2 x cube by 3, and so on up to cn x to the power n plus 1 by n plus 1 plus some constant c. Now, in order to get the result that is asked in this particular problem, so let us put the summation. In order to get the summation, let us put x is equal to 1. So what we'll get if we put x is equal to 1? Okay, so if we put x is equal to 1, this will yield you the result. Okay, this will yield you the uh, correct result. Okay, this will yield you the correct result. And again, if you put x is equal to 0, then you will get to the value of the constant. So in order to eliminate the constant, we will have to firstly put x is equal to 1 and then put x is equal to 0. Or in order to do this in a better fashion, we can write this as in the integration of from 0 to 1. So we can do this, that if we integrate definitely with respect to from 0 to 1, then only we will get the particular result. So the result will be looking like, that is C0 plus C1 by 2 plus C3 by C2 by 3, and so on up to Cn by n plus 1. On putting the limits, okay, 0 and 1, on putting the limits, we get to this particular on the right hand side is equal to the left hand side becomes 2 to the power n plus 1 divided by n plus 1 minus, okay, minus 1, okay, over here, because minus 1 by n plus 1 will be result on putting the lower limit, that is 0. So this result will yield you 2 to the power n plus 1 minus 1 whole divided by n plus 1. So that is the required result that you needed to find out in this particular fashion. Okay, so this is another approach in order to solve problems regarding the summation of binomial coefficient, okay, which has variable terms in the denominator portion, which has variable terms in the denominator. I hope this particular approach is clear. Okay, now let us move further and try out some other approaches, okay, some other problems. So I will take up another example to illustrate what you have learned up till now. Okay, so let me take up the second example, that is, it's again said that C0, C1 and Cn are the binomial coefficient of expansion of 1 plus x to the power n. Okay, so the series that is asked in the problem is basically C0 by 1 plus C2 by 3 plus C4 by 5 plus C6 by 7, and so on up to the even numbers. Okay, and so on. Okay, up to that the result, what is Cn by n plus 1 if n is even number. Okay, so what you can see, all the even lower indices of the binomial coefficient are present in this particular series. Okay, in this particular series, all the even indices are present. Okay, so in order to solve this particular result, how will we do this particular? So what we have learned till now, so if we approach the solution, so what we have learned till now is that if we see the summation of the series C0 by 1 plus C1 by 2 plus C2 by 3, we have did in the previous problem only this particular thing, that is C2 by 3 and so on up to Cn by n plus 1, and this result was equal to 2 to the power n plus 1 minus 1 whole divided by n plus 1. Okay, so this was the result that we have studied. So what we can see from this particular summation is this summation only involves the even numbers, only involves the even number. So for the sake of simplicity, let us consider n is even. Okay, so then I can consider this particular number also. So that means we have to find the summation of all the even numbers where it occurs in the lower indices. Okay, so in order to do so, what we will get? So let us again find out another important series, that is C0 y1 minus C1 by 2 plus C2 by 3 and so on up to minus 1 raised to the power n Cn by n plus 1. So let us try to find out the value of this particular series. So if we are looking for the value of this particular series, okay, now if we are looking for the value of this particular series, how will get this particular series? Now in place of, now what we did in the previous problem, that for this particular, when the coefficient was all added together, we took the expansion of 1 plus x power n. Now when the coefficients are interchangeably subtracted as well as added, the subtraction with the odd numbers and the added with the even numbers, then we can, instead of the expansion of 1 plus x power n, we will take the expansion of 1 minus x power n. Okay, we'll take the expansion of 1 minus x power n, and then we will integrate from 0 to 1, and then we'll get the required result of this particular summation. So I'm calling this particular summation as S1. Okay, or let me call this as S2. This particular summation was called as S1. Okay, so this is S2. So what will generate from S2 by taking this expansion of 1 minus x power n and then integrating it definitely from 0 to 1, we'll basically get the result of S2. So the result of S2 will be, so if we put this particular result, will yield you 1 minus x power n plus 1 divided by minus of n plus 1. Okay, so if we put 0 and 1 over here, so you will get the result as uh, so on solving this, you will get the result as 1 minus 1 divided by n plus 1. Okay, so you'll get the result as 1 divided by n plus 1. So what we can see, that the first the summation s2 is equal to 1 by s minus n plus 1. Okay, so in order to generate the terms which involves the summation of all the even indices, lower indices, so what we can do in order to get the generate result, that is the summation s, so we can do that s1 plus s2 and then divided by 2. This will yield you the proper result of the s, or summation s. So this will give you the result as 2 to the power n plus 1 minus 1 whole divided by n plus 1. Okay, plus 1 by n plus 1 and whole times of half. Okay, so this will give you divide a whole divided by n plus 1 in the denominator and 2 to the power n plus 1 minus 1 and plus 1, minus 1 plus 1 get cancelled, multiply with 1 by 2, and this will give you the result 2 to the power n whole divided by n plus 1, 2 to the power n whole divided by n plus 1. So that is the right answer to this particular problem. Sorry. So the answer to this particular summation is equal to the power n divided by n plus 1. So this particular result will give you the result as 2 to the power n divided by n plus 1. So I hope this particular result was clear. Okay. Now onwards, we will talk about series. Now which will come out in the question is not very simple type of problems that you will face in the examination. So many time in examination you have to try out your brain to understand like what particular summation will yield you this particular result by using the method of concept of coefficient in this particular expansion. Okay, so let us move further and study about, now let us move further and study about the product of binomial, the summation involving product of binomial, sum of product of binomial coefficient, sum of product of binomial coefficient. Okay, so the very first sum of binomial product of binomial coefficient that we already studied was the was very simple result, that is C0 whole square plus C1 whole square plus C2 whole square and so on up to Cn whole square. Now this particular result is very simple to remember. It is equal to 2 to the power 2n minus 2n Cn 2n Cn whole divided by 2. Okay. I'm very sorry. I'm very sorry. Sorry for this particular mistake. This is something different. This is not the result that I'm talking of. Okay. So the result of this particular problem, that is C0 whole square plus C1 whole square plus C2 whole square plus Cn whole square. This particular summation is equal to, now how we will basically is equal to S. So how we will basically deal with this particular problem. Okay. Now in order to get to this is I get as far as remember. Okay. That we studied about in the last lecture only, up to like sum of all the binomial coefficients. Okay. So Cn whole square. Okay. So this particular summation is equal to S. Now the very approach that you must remember in order to solve this types of problem which involve the product of binomial coefficient as a sum. Okay. So what we will do in this particular problem, let us firstly take the expansion of 1 plus x to the power n. So in the expansion of 1 plus x to the power n, we will get the term C0 plus C1x plus C2x square and so on up to Cn x to the power n. Okay. Now again, we can write this particular also by interchanging this particular both the terms as x plus 1 to the power n. So in doing so, what the result will get is that is a very important thing that you must remember is that whenever we take x plus 1 to the power n, we will get yield you the result C0 x to the power n plus C1 x to the power n minus 1 and so on up to Cn x to the power 0. Okay. Now, in order to get the terms which involves C0 whole square, so what we can do, if we multiply this both the summation like this fashion, then we get C0 whole square. Similarly, if we multiply these particular terms, then only we get C1 whole square. And similarly, if we multiply C and these two terms, then only we get Cn whole square. So what we can see that in order to multiply these particular corresponding terms, what we see that we end up getting the coefficient of x to the power n in every time. See, this is x to the power 1 and this is x to the power n plus 1. So if you sum up, we'll basically get x to the power n. Similarly, if you see over here, this is n and this is 0. So summing up, this will become n only. So similarly, x to the power 0 plus x to the power n, this will sum up again to give you the result, that is x to the power n. So what we can say, the required summation that you need to find out this particular problem is nothing but the coefficient of x to the power n in the expansion of 1 plus x to the power n multiplied with 1 plus x or x plus 1 to the power n. That is again very similar. Okay, that is same only, into x plus 1 to the power n, and that is basically similar to as 1 plus x to the power 2n. So we know that result of this particular, that is the summation S will become 2n Cn. Okay, the summation will become 2n Cn. So you must remember this particular result. The result will become equal to 2n Cn. Okay, so the result will be equal to 2n Cn. Now this particular approach will be used in many types of problem statement. So I will take up problems which was already asked in the previous problem, as well as I will take up the illustrations regarding this particular concept of sum of product of binomial coefficient in the upcoming lectures. Okay. Now I will try give you some homeworks regarding this particular types of product of binomial problems. Okay. Okay. Then the homework statement of this particular sum of the product of binomial coefficient will be attached in the description box of this particular video. Okay. Also you can find in the comment section as well. So let us move further and study the new topic that we wanted to study about is the binomial theorem for any index. The binomial theorem for any index. Now, in the today's lecture, we'll only talk about the formula regarding it, and the upcoming lecture will solve few problems to illustrate the formula. Okay, for any index. So what I was talking about till now, that the binomial theorem that we used up till now was that for the index which is basically natural number. Now what if we have we have an rational number? Okay, so what the theorem that I'm writing over here, the theorem that I'm writing over here. So let n be a rational number. So let us n be a rational number and x belongs to a real number. Okay. So n be a rational number and x be a real number such that okay, such that modulus of x is less than 1, such that the modulus of x is less than 1, that is the magnitude of the value of x should be less than 1. And in this particular problem statement, then we can write the expansion, the any expansion of like this particular term 1 plus x power whole raised to the power n, for n is a rational number and x is a real number, such that the value of modulus of x is less than 1. Okay, less than 1. Then we can write the expansion of 1 plus x power n is equal to 1 plus nx plus n into n minus 1 divided by 2 factorial. Okay, n by 1 factorial plus x square, okay, in plus n into n minus 1 into n minus 2 divided by 3 factorial into x square, and so on up to n into n minus 1 whole multiplied with n minus r plus 1, okay, whole divided by r factorial into x power r plus so on up to infinite terms. Okay, so there will be basically infinite number of terms in the expansion of this particular binomial expansion. So this is a very important formula that you will use everywhere. Even in physics also, you will apply this particular formula in order to simplify the result, or whenever you will be approximating results, you will basically use this particular formula. Not every time we will use the formula binomial theorem that we studied only for natural number, but we will basically using this particular formula in most of the situation. Okay. So is this particular result will go on up to infinite terms. Okay, this particular result will go up to infinite terms. Okay. So the condition, this particular condition, that is modulus of x less than 1, is unnecessary if n is a whole number. So that we have already studied this particular term, that if n is an whole number, while the same condition is necessary if n is a rational number. So this particular condition is only necessary if n is becoming a rational number. Rational number. So if n is a rational number, of course we know that the whole number is basically a subset of rational number only. So if we say that if n is a rational number, then this particular condition is necessary. If and otherwise, if n is a whole number also, then this particular condition of modulus of x less than 1 is not necessary. Okay, so this is a very first remark that you must remember. And the second remark that you must remember, that there are infinite number of terms in the expansion of 1 plus x power n. Okay, when n is an negative integer, odd, and fraction. The second remark that you must remember, that the number of terms is basically infinite if n is negative integer or fraction. So if n is a negative integer or fractions, then there will be infinite number of terms. Okay, then there will be infinite number of terms. And the third thing that you must remember, third remark that I will talking about. Okay, in the f of expansion, the first term must be an unity term. Okay, the first term of this particular expansion must be an unity term. If the first term is not an unity term, then you must become, then the index of the binomial is either a negative integer or a fraction. Then we expand. Then in case of expanding the like binomial expansion of x plus a whole raised to the power n, when n is a negative integer or a fraction, then in order to do so, what we do, we firstly take out, we can write this also as a plus x to the power n, and then we take out, right, we take out a to the power n common of this particular bracket, then this will be coming out as a to the power n 1 plus x by a whole raised to the power n, and then we check whether the result of x by a come modulus is less than 1, and then we apply the expansion of this particular binomial expansion, and then we get to the corresponding result. So this expansion can only be expanded when, if and only if this particular condition hold true, if and only if this particular condition hold true. So many times they will face problems where this particular condition doesn't hold true, but you are still on go on expanding this particular relation. So that is very wrong method. Okay, so this particular expansion can only be done, can only be expanded only if and only if, okay, if and only if this particular relation hold true. So what we can see from here, the general term of this particular expansion is nothing but this particular term. The general term of this particular expansion is this particular term. Okay, so this is the very general term of this particular expansion. That is, we call this general term as p r plus 1 as n into n minus 1 into multiplied with so on up to n minus r plus 1 whole divided by r factorial into x to the power n. Now I can give you some idea, right, regarding like how this particular formula come from. Okay, how this particular formula relation came from. So if you look at the summation of 1 plus x to the power n, so where n is an whole number. So the summation was C0 plus C1 x ki power 1 plus C2 x whole square and so on up to Cn x ki power n. So if we look at the general term, that is Cr, so we can expand the general term as okay, n factorial. So this is NCR. Okay, so the NCR, the n factorial divided by n minus r factorial into r factorial. Okay, the general term this was looking like this. So if we look at cancel out the n factorial with n minus r factorial, we can write this as n into n minus 1 and so on up to n minus r into n minus r plus 1. Okay, n minus r plus, sorry, I'm very sorry. Okay, this was n minus r plus 2. Okay, this was n minus r plus 2 and multiply the n minus r plus 1 into n minus r factorial, because we know from the property of factorial, that is n factorial is equal to n into n minus 1 factorial. Okay, so we use this particular property and then we can divide by n minus r factorial divided by r factorial. So if we cancel out n minus r factorial with r factorial, we left out the terms as n into n minus 1 and so on up to n minus r plus 1 whole divided by r factorial. So this is nothing but the similar to the binomial coefficient term only, that we are basically seeing this particular general term before the coefficient of x ki power r. Okay, so this very simple result that we must remember. Okay, whenever we are given with a binomial theorem for any index, check first whether the index is a negative integer or a fraction, and then apply this particular formula by checking whether this particular condition hold true or not. I hope this particular discussion was fruitful. Okay, so I would like to conclude the today's particular description, this particular lecture with this particular topics. Okay, in the next coming lecture, we will talk about the remaining previous topics. Okay, remaining topics like the multinomial theorem and the question regarding it, and also we will solve many problems regarding the summation of binomial coefficient, because that is the most important topic of this entire chapter of binomial theorem. So in the coming two lectures, I will wrap up this particular chapter of binomial theorem. Okay, also stay tuned for the previous year problem discussion on this particular playlist as well. Okay, so if you are someone who is new watching this particular channel for the first time, then I will request you, if you are liking this particular content, then subscribe to my channel and as well as like the video. If you are new, also subscribe as well as press the bell icon. Okay, so with this, I take a leave from today's lecture and thank you.